All right, we're going to continue our discussion of springs. By looking at a really simple case. So what we've got, this will allow us to do a couple of things. We're going to have a spring at the bottom of a ramp, spring constant K. We're going to take a mass of M and we're going to drop it. Now it's going to be frictionless. We have a height of H. We're going to let it slide down. And this is an example I think that we did last year. It's going to slide down and it's going to hit. So first thing we want, find the speed of the mass at the bottom. So, looking at this, at the top, the energy at the top is gravitational potential energy. And then when we're down here, at the bottom, energy at the bottom is kinetic energy. So, to get the speed at the bottom, we set that gravitational potential energy equal to the kinetic energy. mgh is going to be 1/2 mv squared. The m's go away, and so this velocity comes out to be the square root of 2gh. Very straightforward problem. The next thing, find the compression of the spring. So for that, we know this thing is eventually going to run into the spring, hit it, compress the spring a little bit, and my mass is going to be back here. And we're looking for that amount of compression. So when that happens, the energy in the system is now stored as spring potential energy. So, energy 3, I guess we can call it. So really, the total energy is equal to energy at the bottom is equal to energy 3. So we can say mgh is equal to 1/2 kx squared. We could say 1/2 mv squared is equal to 1/2 kx squared. We just have to plug that velocity in again. This is the simplest one. So we're going to solve for x this time. That's our compression. So 2mgh over k square rooted gives me that compression. Now, in real life, what's going to happen with this, thing slides down, compresses, and then gets shot back up. When it's shot back up, it goes back to the height h, slides down, compresses the spring, and is shot back up. As long as there's no friction on this system, it's going to continually go down and shoot back up. That's a simple example. We're going to move on to something a little bit more complicated. We're going to take a spring. We're going to take a spring and we're going to attach it to the ceiling. We're going to let it hang. There's a hook on it. Well, and we're going to take and we're going to attach a massive M to that spring. So what's going to happen is our unstretched spring is going to extend all the way down. So basically the mass is going to fall and eventually stop. So the first thing I want is this distance. We'll call it h. I want to know how far down the mass falls. how far does it fall? So we're going to look at the energy here. All of my energy at that point is gravitational potential, and the energy down here, spring potential, and set those equal to each other. So gravitational potential is mgh, and that's going to be equal to the spring potential, 1/2 k times the distance that we stretch the spring squared. Well, in this case, my spring goes from being this long to this long. That's a difference of h, so it's 1/2 kh squared. So one of my h's cancels out, and if we solve for h, it's 2 mg over k. That's going to be the bottom of this point. Now, what's going to happen is that mass is going to shoot back up. It's going to compress here, and then it's going to repeat the whole process over and over and bounce up and down. Now, eventually, it will come to rest a little bit lower than where we started. We'll call that distance A. Find A where the spring is at rest, or where the mass is at rest. So when the mass is at rest, the net force acting on it is 0. Pulling up, we have kx. Pulling down, we have mg. So we can say that force of the spring is equal to the weight, or kx is equal to mg. So x is going to be mg over k. And we see that this equilibrium point, and let's call it that, this equilibrium point is halfway when compared to how far down this thing goes. Something to think about. Now, eventually you're going to have to deal with, and yeah, I meant to draw this one slanted, a spring on an incline. So if that's the case and the thing is bouncing back up and down, and we're talking about sort of this distance x, well, that's going to say something about spring potential, but that's going to correspond to a height that's equal to x times the sine of theta. There's just one thing to remember about springs. Now, these should be fairly straightforward problems. They're going to get more complicated when we talk about simple harmonic motion, but that's just a little thing that we're going to add on to here. It's not too big of a deal. So, that's it for springs.